Hey Wheaton North, Mr. Yergler here. We're going to introduce equilibrium by talking a little bit about lemonade. When I was a kid, this was before I was even in kindergarten, my brother and I made a lemonade stand. We lived in Arizona at the time, so it was always really hot out. We lived in a cul-de-sac, so we didn't exactly get a lot of foot traffic. It wasn't really the best location in hindsight. But anyway, we made this lemonade, and my brother sent me into the house to go get more sugar because he didn't think it tasted right. So I go and grab the sugar, we add a bunch of sugar to it, we mix it up, it still doesn't taste right, so we dump even more sugar in and mix it up, and it's getting worse. So we figure the only solution is to add more sugar. So we added even more sugar into it. We're just dumping sugar in, right? Mixing it up, it's like a saturated solution. And then we taste it again, and it's super duper terrible. And finally my brother tasted the sugar, and he said, "Mr. Yergler, this is salt." And that was the beginning of my chemistry education. But anyway, I want to use the example of lemonade to talk about equilibrium. Why is lemonade 10 cents? Why is it so cheap all the time at these lemonade stands? Why isn't it like $10? The answer is equilibrium. There's an equilibrium between supply and demand, right? This is true of anything in anything that's for sale. There's always an equilibrium between supply and demand. Same thing with like the latest iPhone. Why is it so expensive? Because people continue to buy it. If people stop buying it, then it would get less expensive. There's always this balance between supply and demand in any economic situation. And as long as those stay consistent, then the price doesn't fluctuate. So the equilibrium can kind of be described by the price. We often say that equilibrium is dynamic, which just means that it's not static. It's constantly influenced by outside factors. So there's a lot that goes into economics, but in short, if the supply rises or if the demand rises, then that affects the equilibrium. It shifts the equilibrium, which is basically the price, either up or down. So tons of different outside factors can stress the equilibrium, right, or stress the system. I'm going to use the word stress to kind of mean apply pressure to the system. We'll come back to the idea of stressing the system later. As long as those outside factors remain consistent, then the equilibrium stays constant and equilibrium is reached, right? As soon as anything changes, then we get a new equilibrium. This is true of supply and demand. It's also true in chemical reactions where the outside factors are more something like temperature, concentration, or pressure. All right, so let's take this generic equation here. Most reactions are reversible, and so we represent that with double arrows. And equilibrium is the state where the rate of the forward reaction is equal to the rate of the reverse reaction. Notice that I'm underlining, bolding, and italicizing rate. Okay, I don't mean that the concentrations are the same. In fact, the concentrations are rarely the same. And it doesn't mean that the forward and reverse reactions stop. Once we reach equilibrium, it's not that we stop producing C and D. It's that we produce C and D at the same rate or equally as fast as we're producing A and B. And that's kind of shown in this graph. Notice that the concentrations are not the same, right? The products are much higher in concentration than the reactants. But the point at which they stop changing is the point at which the forward reaction becomes equal in rate to the backwards reaction. And that's where you would see no concentrations changing, right? The concentrations remain the same. So in this generic equation, we could say that the reaction can lie far to the right, like this, where we have lots of products but only a little bit of reactants, but it could still be in equilibrium. Or we could say that it lies far to the left, right, where we have lots of reactants and only very little products. Again, still at equilibrium. That doesn't mean that we're producing A and B faster. It just means that when those outside factors balance out, we happen to have more of A and B and less of C and D. The factors that affect this are temperature, relative energies of reactants and products. This is referring to mostly the energy of the bonds themselves, right? Nature is going to gravitate towards a lower potential energy. And then the degree of organization or disorder. And this is referred to as entropy. We're going to get into that later. All right, so the equilibrium expression, sometimes you'll see it referred to as the law of mass action, is essentially the ratio of products to reactants. Okay, so it's always the concentrations of the products over the concentrations of the reactants. You might want to write that off to the side. Products over reactants. Never forget that it's products over reactants. And then the balanced equation coefficients become exponents in that equation. Okay, so it looks similar to a rate law, and we're even using the same letter. K is always used to refer to constants. but it's pretty different from a rate law. We're not saying, this doesn't tell us anything about the rate. It tells us about the concentrations, the relative concentrations of the products and reactants when they reach equilibrium, when the concentrations stop changing. And this is kind of a big note here. It excludes pure solids and pure liquids. The reason is that you can't really have a concentration of a solid, right? The concentration of a solid is mass you have in a certain amount of volume, right? What is that? That's basically the density. And so that's going to be constant anyways, right? So it kind of gets wrapped into the constant itself. Same thing with liquid. The concentration of a liquid is essentially just its density. Another side note, you'll see multiple different Ks. Sometimes it's just a generic K. Sometimes it's Kp for pressure. Sometimes Kc for concentration. Sometimes Keq for equilibrium. This is kind of a minor point. Occasionally you'll see questions about manipulating K. Let's use this example here. If you were going to write the K expression for this, it would essentially be this. Take the products over the reactants. Remember to use the coefficients from the balance equation as your exponents, right? So H2 is raised to the third power. N2 has no power because it's just a 1 here. Occasionally you'll see equations written with like fractions, or sometimes we'll have to double an equation or something like that. In this case, the K expression is still written the exact same way, but now that your coefficients have changed, your exponents change, right? So it kind of becomes something like this, where now NH3 has just a 1 for an exponent, and then I put 1.5 instead of 3/2, just to kind of make it look a little neater, and 0.5. We can also, you'll see this more often, we can also reverse reactions, right? In fact, all of these reactions are reversible because they're at equilibrium. So it's kind of arbitrary whether we write it this way or reverse. Okay, so if we write it this way, our K expression would be like this, right? Just like it is up here. But if we were to write it the other way, where we start with the NH3 and we're going to N2 and H2, now our K expression is written like this because it's always going to be products over reactants, right? So our two products, now we have two products over the one reactant. Notice how this K expression is really just the inverse of this K expression, right? And so the K of the forward reaction is equal to the K of the reverse reaction, but flipped. All right, another kind of minor point, you'll see this occasionally. Kp and Kc often seem interchangeable, and in some cases they are, but not always. This is a formula that is used to kind of make the conversion. This is a derivation of the ideal gas law. So this is the ideal gas constant, which is 0.0821, and then our temperature in Kelvin. The delta N is the change in moles of gas, okay? And this is kind of the main point that I want you to take away from this. Kp and Kc are the same if there's no change in the number of moles of gas from the reactant side to the product side. So delta N would basically become 0, so then this whole section of the equation becomes 1, and then Kp equals Kc. Look at this example. In this case, we have 11 moles of gas on the reactant side, but only 10 moles of gas on the product side. So your moles of gas is not staying the same, right? And so you would not be able to say in this case that Kc and Kp are equal. Go ahead and pause the video and write an equilibrium expression for this reaction. All right, you should have gotten this right here. Make sure you have all your exponents. Which version of K, Kp, Kc, Keq, makes the most sense in this case? We're dealing with gases, and so it makes sense to use pressures, and so Kp would be appropriate. You could also write it like this, where we're kind of dealing with partial pressures, the partial pressure of each reactant or product. Another example, so write the Kc and Kp for the following process. Decomposition of solid phosphorus pentachloride to liquid phosphorus trichloride and chlorine gas. Just from those names, you should be able to get this formula. And now looking at this, what would be your K expression? Make sure you leave out the liquids and the solids. It's just the concentration of Cl2. So then the Kp would just be that pressure of that. And that's it. So if you have any questions about K expressions, make sure you write those down now. And this is Mr. Ugler signing out.